Good morning. Today we are going to start with the next topic, that is graphical representation of complex numbers. Now we use a plane called as Eigen Plane to do the graphical representation, and the actual representation is called as the Eigen diagram. Just as we know that given any two-dimensional Cartesian point which we usually write as x comma y, we can denote it graphically on the xy plane, which are two mutually perpendicular directions, x axis and the y axis. Same way in the Eigen diagram and the Eigen plane also, it consists of two mutually perpendicular directions, the horizontal, which is x axis, is called as the real axis, and the vertical axis, which is usually the y axis, it depicts the imaginary axis. So in case of an Eigen plane, there are two mutually perpendicular directions. One is the horizontal direction called as the real axis, which is actually the x1, and the vertical direction called as which is called as the imaginary axis, which is actually the y axis. Now accordingly, given any complex number, let's say z equal to a plus ib or z equal to x plus iy, we can associate an ordered pair with this. So if we are writing z equal to a plus ib, in this the real part is a and the imaginary part is b, and we associate an ordered pair a comma b with this complex number. Now here we call it an ordered pair for two reasons. First is that pair means two, and here we are writing two members, one is the real part and one is the imaginary part, and ordered means in a particular order. So it is a fixed thing that we first write the real part and then we write the imaginary part. So hence this is called as an ordered pair. Similarly, if the complex number is written in the form x plus iy, the real part is x and the imaginary part is y, and the ordered pair corresponding to this would be x comma y. And we can draw the Eigen plane as this is the horizontal axis called as the real axis, where we plot the x coordinate, which is actually the real part. So here this is the x axis and this is called as the imaginary axis, which is actually the y axis. So corresponding to this point, let's take this as the complex number. So you will have a as the x coordinate and b as the y coordinate, and let's denote it by point P. So a comma b would be somewhere here in case both a and b are positive, and so this is the origin, which is the point of intersection of the real axis and the imaginary axis. Now we proceed further. So this is called as Eigen plane, and when you plot this point and you join this point to the origin, this becomes, this whole thing, the plane along with this point and this line joining the point to the origin, it becomes the Eigen diagram. Now in case of Cartesian coordinates, if you are associating x and y with z, so this point could also be x comma y. These are the Cartesian coordinates, and this z equal to x plus iy is the Cartesian form of writing the complex number. Now again, just as in the Cartesian plane, which is the xy plane, there are four quadrants. Same way here also there are four quadrants. This is the first, this is the second, this is the third, and this is the fourth quadrant, exactly on the same. The only difference is here along the y axis we are plotting the imaginary part, whereas along the x axis we are plotting the real part of the complex number. Rest all is the same. So, here in the first quadrant we have both x is positive and y positive. Here in the second quadrant we have x is negative and y is positive. Here both x and y are negative, and here we have x is positive and y is negative. Likewise, if the number the complex number is something like z equal to 2 plus 3i, clearly the ordered pair which is associated with it would be 2 comma 3. Both are positive, and so it will lie in the first quadrant. Okay. So, in order to show it graphically, we will draw the Eigen plane something like this, and the diagram now becomes, since the point is somewhere over here, we write 2 comma 3 and we join it to the origin. This is the x axis, this is the y axis. Now, suppose we take z equal to minus 2 plus 3i. So, the ordered pair corresponding to it would be minus 2 comma 3. Clearly, it will belong to the second quadrant, and so the Eigen plane or the Eigen diagram corresponding to it would be something like this. This is x axis, this is y, and here it will this point will lie somewhere over here. So, you write it as minus comma 3, call it point P, and this is the origin. Now, in case we have z equal to minus 2 minus 3i, the ordered pair corresponding to this would be minus 2 comma minus 3. This will lie in the third quadrant, and so the Eigen diagram would be something like, the point lies here, which is minus 2 comma minus 3. You join it to the origin. This is x axis, this is y axis, and so this is the corresponding Eigen diagram. And the fourth quadrant, suppose z is somewhat like 2 minus 3i. So, the ordered pair corresponding to it would be 2 comma minus 3, which belongs to the fourth quadrant, and the figure would be, or the Eigen diagram would be somewhat like this. This is origin, this is x axis, this is y axis, this is the point which would be 2 comma minus 3, and you join it like this, and this is the corresponding Eigen plane. Now, let us proceed slightly more and see what is the modulus, and we had discussed in the previous topic before the first exercise, we had discussed something called as modulus and conjugate of a complex number. Now, given any, so let us write modulus and conjugate of a complex number. Now, we know that, let us take any general thing. Suppose we are taking it in the first quadrant only. So, x comma y, and this is origin, this is x, this is y. Now, by modulus we mean the length of the line joining the point to the origin, and so this is called as the modulus of the complex number x plus iy, and the modulus of z is denoted by mod z. Now, here from this, if you drop a perpendicular to the x axis, let us call it n. So, very obviously, if this is the x coordinate, this length becomes x. If this is the y coordinate, this length becomes y. So, OP would, now by Pythagoras, since this is a right angle triangle, OP square would become x square plus y square, which gives us OP is equal to under root of x square plus y square, but OP is mod z. So, modulus of z is equal to under root of x square plus y square. So, this is the meaning of modulus of the complex number which we had discussed earlier. Another thing, if you observe x comma y, suppose we consider now conjugate of z is equal to z bar would be is a number obtained by reversing the sign of the imaginary part. So, x minus iy is the conjugate of given z. Now, if you plot this on the same Eigen diagram, what do we observe? This point, let's call it P dash, it will be x comma minus y, and if you observe carefully, it is nothing but the mirror image of the point x plus iy, which is xy, about the x axis, treating this as the mirror. So, what do we conclude? That conjugate of a complex number is the mirror image of the given complex number. Okay. Now, let's consider the next topic, and a very important topic, which is polar representation of a complex number. So, polar representation of a complex number. Now, here this is another way of writing a complex number. So, we have all this while we have studied the complex number in the form x plus iy. So, we can associate a pair x comma y with this, and these are called as the Cartesian coordinates. Same way we have polar coordinates, which are called as r comma theta. Okay. So, the representation of z in terms of r and theta is called as the polar representation. Now, what is r and theta? So, given this complex number, we can write, we can draw the ARGAND diagram for this as, suppose this x and y are both positive. So, the corresponding point is xy, which lies in the first quadrant. You join this. This is the origin. So, the length of OP, or the magnitude or the modulus of OP is called as the magnitude of OP is called as the modulus of z, which we have just studied, that we call OP as mod z, and this we denote by r. So, basically polar coordinates are r comma theta, polar coordinates are r comma theta, where r is the radial distance of the point from the origin. Radial distance of a point from the origin, that is, if you join the point to the origin, this distance OP is called as the r, is denoted by r. But as we have already seen, OP is nothing but the modulus of the complex number, and so OP is equal to mod z is equal to r. Now, theta is always, now we will follow two rules for finding theta. First thing is, theta is always measured from positive x axis. Second point is that theta is always taken as positive when it is measured in the anti-clockwise direction, and it is taken as negative when measured in clockwise direction. Now, what is the meaning of this? The meaning is that here this is the positive x axis, okay, what is theta? First of all, theta is the angle which the line joining the point to the origin, that is OP, makes with the positive x-axis. Okay. Now, here when the point lies in the first quadrant, to be able to reach OP from the positive x-axis, we have to execute this angle in the anti-clockwise direction, and so here the theta is positive. Whereas, suppose we had, let's take the suppose the point was, or let's take another point which is x comma minus y, suppose it was in the fourth quadrant, then to be able to reach OQ, we would have had to execute the angle in the clockwise direction, and so here the angle would be negative. Okay. Now, as we can see, the four quadrants cover an angle equal to 360 degrees. Those 360 degrees can also be covered if we start from here, that is the negative x-axis, and reach this side, and then again cover this whole angle. So, instead of starting from the positive x-axis, like instead of taking the angle as theta lying between 0 and 360 degree, we do not take this way, we take theta lying between minus 180 degree and plus 180 degree. So, this is the called as the principal value of theta, principal value of theta. It lies between, so we do not take, see, the whole idea is to cover this full 360 degrees. It can be covered if you measure the angle from here and back to here, or it can be covered that if you measure the first half, means the first and the second quadrant in the anti-clockwise direction, and the fourth and the third quadrant in the clockwise direction. So, that here the angle lies between 0 and minus 180, and here the angle lies between 0 and plus 180. So, the entire range of theta becomes minus 180 to plus 180. So, and when the point is here, obviously this angle can be executed in the anti-clockwise direction and make it as plus 180, or it can be executed in the clockwise direction to make it minus 180, but we consider this 180 degree for this line negative x-axis and not minus 180. So, this is another point which we take for theta. Now, theta is called the argument or amplitude of z. So, with theta as this and r as this, the pair, ordered pair r comma theta, therefore it is called as the polar coordinates, and polar representation is nothing but the representation of z in terms of r and theta. Now, let us see how do we write. So, we will be checking, or we will be writing x and y, we will find a relation between x and y and r and theta. So, let us again take the polar diagram, sorry, the ARGAND diagram, and let us take the simple case of first quadrant. Okay. Suppose this is theta, you drop a perpendicular, this is x, this is y, we know this is r, this is x and this is y. Very clearly we can see that in this right angle triangle, we have, let us say this is N. In triangle ONP, we have x upon r equal to cos theta and y upon r equal to sin theta. This gives us x equal to r cos theta, and this gives us y equal to r sin theta. So, if you know r and theta, you can find the value of x and y. Now let's see the other way round. That is, if we are given x and y, how do we find r and theta? So let's call it equation number 1, let's call it equation number 2. So squaring and adding 1 and 2, we get x square plus y square equal to r square cos square theta plus r square sin square theta, which gives us r square cos square theta plus sin square theta. But we know that cos square theta plus sin square theta is 1, and so this gives you x square plus y square equal to r square, which gives us r is equal to square root of x square plus y square. This is another way of finding r in terms of x and y, though we have found it using the Pythagoras theorem earlier and we got the same answer. Now to find the argument theta, what we do is you divide 2 by 1, we get y upon x equal to r sin theta over r cos theta. This gets cancelled and we get tan theta equal to y upon x. That is, tan theta equal to imaginary part of z upon real part of z, and this gives us accordingly whatever value you get, the corresponding value of theta is the required thing. So with this we have done, or you have been introduced to the polar coordinates r theta, and we have already discussed the relation between x and y, the Cartesian coordinates x and y, and the corresponding polar coordinates r and theta. In the next video we will be studying how to convert the given polar complex number in the polar form. Thank you.